Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's biweekly contest, minimum total cost to make array unequal. The problem is bit tedious. I myself was not able to solve this problem during the live contest. Uh, the problem is ad hoc, so it doesn't mean that if you are not able to solve this problem, it doesn't mean that you don't know how to apply certain algorithms in this case. Like ad hoc problems are like this. I can even point out to ICPC regional online round contests where in 2018 there have been ad hoc problems similar to this, very similar to this, and only few people were able to solve this. Like only few teams were able to solve this. So ad hoc problems are like this. You have to make right observation and you have to have knowledge of similar ad hoc problems or ad hoc properties beforehand to solve this kind of problems. So it's completely okay if you're not unable to solve this during the live contest. But most importantly, you should learn certain things from the problem as always, and pick them pick them in the toolbox whenever needed in the future. So with that, like we will be focusing mostly on the proof, as this problem doesn't require any kind of algorithms, right? So we'll be focusing mostly on the proof and a bit of intuition on how to approach this kind of problem in future. Okay, there will be one proof which we'll not be discussing. We'll look at that, but I will definitely point you to the correct blog posts and correct videos which you can watch to understand the in-depth proof. So with that, let's get started. The problem states that you are given two arrays, nums1 and nums2, each of which is of length n. You can swap any two indices of nums1, and the cost of this swapping is the sum of the indices. Okay, so the final target or the final goal is to make every index of nums1 not equals to every index of nums2. Okay, so finally this condition should hold true for all I. So you need to return the minimum total cost. Like you can apply this operation, you can apply this operation any number of times, right? So you have to return minimum cost. Notice you have to you have to return the minimum cost, not the minimum number of operations you will perform. You have to return the minimum cost such that this condition will be satisfied at the end. Okay, so it may be the case that this condition would not be satisfied. In that case, you will return -1. Okay, so let's like the problem is very straightforward. You just need to like swap is the operation, and the cost of swap is sum of indices. So let's look at an example quickly. These are like this is num1 and num2. Every indexes are equal, so you need to rearrange every indexes here so that they final arrangement would not every index of final arrangement would not be equals to the indexes in nums2. Okay, so one of the optimal approaches that they have took is they have swapped 0 and 3. So you swapped 0 and 3. So finally you will get 4 2 1 4 2 3 1 5, right? And similarly after that they swapped 1 and 2. So after swapping 1 and 2 you will get 4 3 2 1 5. And finally they swapped 0 and 4, uh, 0 and 4, and after swapping this they get 5 5 3 2 and 4. So this is like this array, like you can see 5 is not equals to 1, 3 is not equals to 2, right? And similarly 2 is not equals to 3, 1 is not equals to 4, and 4 is not equals to 5. So the condition is satisfied, and the cost here is the first operation cost 0 plus 3, which is 3. Second operation cost 1 plus 2, which is again 3. Third operation cost 0 plus 4, which is 4. So in total the cost is 10, and you can apply any other operations to make this condition satisfy, and you will notice that you can't make you can't make this they make this condition true in less than 10 cost. Okay, so hence 10 is the answer. So hope the problem statement is clear. Now how to solve this? So again, we have to make some kind of observations here. There is no intuitive way to solve this kind of problem, as we already discussed in the disclaimer of the video. So first, let's make some observation. Like, let's start with some obvious observations that you should be able to make while looking at the problem. So you can swap two indexes here, right? Or first of all, like you can see, there are duplicates as well in the given array, because the constraint doesn't talk about duplicates at all. So there can be duplicates in the given array. Now, because there can be duplicates, the solving this problem or this version of problem is bit difficult. So you should always, as always, you should try to think of reducing the problem, and let's solve the problem where all the elements are distinct. So something like this, right? Now, what you have to swap elements, right? So you can see here these three elements needs to be reordered such that uh, they become not equals to the corresponding nums2 index, right? Now you can swap index. Let's say this is I and this is j, right? The index of this is I and index of this is j. Will it ever be the case that you will swap I with some k? Let's say this is k, right? Let's say, will it ever be the case that you will swap I with k, and then you will swap j with k? Like, will this ever be any case like this? Answer is no. Not completely no, but for now answer is no. The reason being, uh, this will cost you I plus k, right? And this operation or this swap will cost you j plus k, right? So in total, your cost is equals to I plus j plus 2k, right? Now, how about you just swap it I and j by themselves? Like you just swap it I and j in one operation. In that case, the cost would be I plus j. So you are paying extra 2k cost for this exact same arrangement. Like after this arrangement, only I and j will be swapped. The position of k would remain intact, right? So you are paying extra 2k cost for exact same arrangement. So will you ever be paying this 2k extra cost? Will you ever will be willing to pay this 2k extra cost? Surely not, right? So that's where this is the first observation where we should always try to arrange, like we should always try to arrange the elements among themselves whenever possible, because arranging among themselves which will actually lead to lesser cost, right? Now there is a uh, like this is the statement that we just derived. Now there's a catch here in this equation. The catch is, what if k is 0? If k is 0, then this I plus j, like this entire thing would evaluate to I plus j, which is the exact same cost we are getting if we swap just I and j, right? So what does it mean? It means that we can just think of zero index as a temporary variable always. What we can see, what we can do is, let's say, if we have one index to be swapped with, let's say this is the index that I want to be swapped, like this index and this index, right? Now if these two index we want to be swapped, we can just like either we can swap them directly, right? Or we can think of that we'll always use zero index to swap it. Like we'll always use this kind of arrangement to swap it. And why we are doing it? The reason is it makes swapping simple. So if we always think of, like if we try to do this thing, like we try to arrange elements among themselves, it is difficult because you need to match pairs, like I with j. You have to find all i's, all possible i's and j's that are optimal, right? But this is difficult, but if we are taking this k as a temporary variable where k is always 0, then we can simply say that we don't need to find pairs. We can just see which position we need to change, and we can just swap it with the corresponding other position which we want. So for in this particular example, we saw that 3 and 5 uh, both needs to be swapped, right? So what we did, we just swapped 3 with 1 initially, and then we swapped 5, like 5 with the same one. So the reason it works here is all the elements are distinct. So swapping only will help, like if we just swap, like we are swapping 3 with 1, right? So if we just swap this particular thing, that alone is sufficient to tell that the final arrangement would not be equal, right? So basically we are removing 3 from here. We are removing 3 from here and something else will come here. And we are ensure, like we have already assumed that all the elements are distinct. So if something else comes here, that would not be 3. And if it is not 3, then only our condition is satisfied. So what we are saying here is, uh, we can use k, or we can use this index 0 as a temporary index to swap everything, right? Now, um, let's relax this constraint where all the elements are not distinct. So in this particular case, what will be the answer? Like if all the elements are distinct, then what will be your answer? The answer would simply be uh, the sum of all the indexes which are not equal, right? So in this case, 1 plus 4, right? One, what you will do, you will just swap this 3 with 1. You will get 1 here, and 3 will come here, and then you will swap 3 with 5. 5 will come here, and 3 will go there. So that will be your answer. And the reason it works here is because every elements are distinct. So if every element is distinct, you just need to swap the values, like swap the indexes which are not equal, right? So now let's just relax the constraint. So if we relax the constraint here, so sorry for this. So if let's say if we relax the constraint here and there are duplicates in the array, now you can't say that okay, only swapping this with 0 would make things easier. So for example, you can swap 2 with 1, right? And 2 will come here and 1 will come here, right? Now again, you if you swap 2 with 2, 2 will come here and 2 will come here. So this element itself doesn't change. So that's the difference, right? So if all the elements are not distinct, which is the case in the given problem, we can't apply the same approach that we have just discussed, right? So what exactly we need to do? We need to now find the pairs. Like previously we skipped finding the pairs altogether, but now we have to form pairs. Like we have to form pairs from the given like from with the given set of non-matching indexes, right? So in this particular example, there are two twos here, right, and one 5 here which doesn't match. So these are the three things which needs to be rearranged. Now you can think like you can swap one from here and one from here. That is fine. Like you can swap this one of these two with one of these 5. So that is okay. So you can now which one to swap? The answer is it doesn't matter, because if you swap the first two, right, whichever two you choose, both of these would contribute or would be added once in the answer. So whichever index you choose, index doesn't matter here. So both will contribute to the answer. So that's where we will just find out the frequency here. Like we just care about the frequency here, right? Again, just to reiterate why this pair or why the indexes doesn't matter here is we have let's say the positions are I, J and K, right? I and J. The two position of these two twos are I and J. Now, whenever you swap this I with something, let's say K or some K dash, you will be contribute like what will be contributed to your answer I plus K dash, right? And similarly, when you will be swapping this J with some, let's say K double dash, you will be contributing J to the answer. So in a way, I will be contributed and J will be contributed always, no matter what, right? So that's where what you can say is the positions of these twos doesn't matter at all. What matters is how many twos are there and how many fives are there, and now we need to make pairs out of it, right? That's it. So we will like this I and J will always be contributed no matter what, and along with this I and J, something will be contributed, and this something will we'll look at afterwards. If it is something which we are swapping with already, then it is also taken care of. Let's say we are swapping this 2 with 5. So for 5, we have already added k dash to our answer. So this is taken care of. But if we are swapping, let's say this 2 with this 5, then this 5 is not taken care. Like this 5 is not added to the answer at all. So we need to take care of that explicitly. But for now, what we are saying is we are just caring about the positions which are not matching. So all of these would be there in the answer for sure. So we will just accumulate all of this into our answer variable beforehand, right? Now after accumulating them, what we need is we need to just find the pairs, and let's see how we'll do that. So basically we have two twos. Like now frequency matters only. We don't care about the position, so only frequency matters. So there are two twos and there is one five, right? We need to make pairs. We need to make pairs. So now how you will make pair? You will just pick the largest, the value with the largest frequency, the first two value the largest frequency, and just make a pair out of it. So what you will say that I will just I will take 1 2 from here, 1 5 from here, make a pair. So number of fives remains is 0, number of 2 remains is 1. So again what we are saying is this 2 denotes that there are two twos for which nums1 and nums2 were equal, or there are two indexes for which nums1 and nums2 are equal and the value was 2. Similarly, there is one position where nums1 and nums2 is equals to 5. Now we already have added those positions to our answer. So we don't care about their actual positions in the array. We just care about their frequencies, right? Now we need to make pairs. Now what how we are making pair? We just make 2 and 5 as a pair. So what we are saying is we just swapped one of these two with one of these 5. So because 2 and 5 are swapped, initially these two were equal. Nums1 and nums2 are equal and they were 2. And nums1 and nums2 are equal and they were 5. Now we swapped one of these 2 and 5. So this will become 5 and this will become 2. So in a way, our array would become like our condition would satisfied for these two indexes. And that's where we reduced these values from here. So we'll do this similarly if there are more frequencies as well. Let's say there are threes as well. Just for example, let's say there are two threes as well. So in this case, what will happen is there will be there will be two threes as well. So now when you start making pairs, initially you will pick two largest one. So you will pick this two and this two, right? And you will make pair out of it. So you will swap two and three basically. You make pair out of it, and this will stay one, right? And now again you will pick the two largest one. So again two and five, let's say you make pair out of it, and now finally this three remains. So this would always be the case. There will be always one element. Either everything will matched up completely, right? Or there will always be one element which will remain at the end, right? And this will be only one element, right? So this is very standard process. I think you might have encountered this already in other contests as well. Like you just use priority queue and just take the maximum two value and just keep on subtracting them. So that's how you do pairing, optimal pairing. Now after that you will end up having one value only, right? Or one index only which is not which is not swapped, and it is still equal in nums1 and nums2. So now this value can be 1 or it can be greater than 1. It can be all 3 as well, right? So now what exactly we need to do here? So let's talk about the case where it is 1. So the value is 1. So we are like after pairing everything, we left with one pair which we left with one index which is not getting paired. So if we talk about a specific example, let's just get rid of all of this. uh, so let's just remove all of this as well, right? So if we talk about a specific example, in this case, these two, let's say, remains as is, and this 2 and 5 getting swapped. Okay, so now this 2 and 5 getting swapped, and this 2 become 5, and this 5 becomes 2. So these two indexes are now okay, and this 2 is the one that remains. Now what you can do, if you remember from the previous observation, that we can use 0 always without any extra cost, right? So like now there are two choices. See, you can swap 2 with 5, or you can swap this 2 with this, right? So first of all, you can't swap with whatever was rearranged, right? Because you already rearranged it and you don't want to touch it at all. Otherwise they might be uh, like their positions might get distracted, and whatever you rearranged might not be true. So you don't want to touch whatever you have rearranged. So you have only two choices. You have this index and this index. Now you can't rearrange the, like you can't swap it with an element where nums of I is equals to 2, right? Like nums1 of I is equals to 2, because if nums1 of I is 2 and you're swapping it with current 2, there is there, like the final arrangement would still be same, and this pair would still exist, right? Similarly, you can't swap it with something where nums2 of I is 2. So for example, let's say if you decide to swap this 2 with this 5, then this will be satisfied, this will become 5, that is okay. But this, if this 2 goes here, then you will form a new pair. That is also something that you want to avoid. You don't want to form new troubles or new pairs which doesn't match, right? So these three conditions would be there. So after these three condition, there is only one index currently, but there can be multiple indexes as well. Let's say there are like some other indexes as well which satisfies all these three condition. Like now, which one you will choose among these three? The answer is you will always choose the first one, right? You will always choose the zeroth one. Now, what's the advantage? Like you can, uh, because you are choosing the zeroth one, you can get it for free because k is zero here, right? Now there might be case where this 2 comma 2 pair is itself at position 0. In that case, you will choose the first, like first position that occurs, right? So that's the entire solution. So what we will be doing is we will be just taking out pairs, trying to assign them or rearrange them, right? And then we will just see what we have remained with, right? And whatever we have remained with, we will just iterate again through the entire array and just see which on, as we will be remaining with only one pair, right? Only one pair or only one value, we can just see which all indexes are valid based on these three conditions. And among all these indexes, we will just take the first k. Like let's say this value is k, we will just take the first k out of them, right? And that is our answer. So there are some edge cases, but we'll talk about it. But let's first look at uh, a like big example. So let's say this is our array nums1 and nums2. Now if you look at it, there is only two positions which are okay, others are not okay, right? And these are the pairs, like 2 2 is there at position 1 and 2. So at position 1 and 2, there is inequality for 2. Similarly, at position 7, there is inequality for 3, and so on and so forth, right? Now, as we discussed, we initially go ahead and add all this position already to our answer, right? So initially, what we have is 1 plus 2 plus 7 plus and so on and so forth. Like this entire thing is already there in our result, right? So let's just take 1 plus 2, 3, 10, 14, 19, 28 and 36, 46 and 54. So currently result is 54 already, right? Because we need to swap these elements at least once. So this will be there. So 54 is there. Now, if we just try to build our frequency map again, so there are two twos, right? There is one three, there is one, two, three, four, five, six fours, right? And there is five, there is one five. Now, again, you will apply the same thing, like you will just take the maximum frequencies first, right? And apply, make pairs out of it. So you will be having 5, 4, 1, 2, and then you will took like this 2 and 6 is gone. Now you will took 5 and 1, any one, right? So this 5 is gone, this 5 is gone, this one is gone, this is 0, and this is 4 now, right? Now you will took, let's say, 4 and 1. So this will become 3, this will become 0. Now let's say you take this and this will become 2, and this will become 0, right? Now what you remain with is there are two fours which still remains and needs to be mapped out. So two fours are remaining, right? Like fours are remaining. Now what are the positions which were left? Positions which were left were 3 and 11. Now, okay, let's assume that here it is 4, right? Now if here it is 4, you have only one position, and now you have two elements that you need to be swapped. So answer is -1 in this case, right? Otherwise, if there is, let's say, one position, there are two positions and or greater than two positions, and there are two elements here, you will just take out the minimum or the minimum two, right? You will just take two, and let's say there are other elements as well, like 12, 13, and as well. So you will just take the minimum value, because if you think these two would be swapped with this third position and 11th position, so this 3 would be added to the answer, and this 11 would be added to the answer, right? So you want to take the one which add minimum to your answer. So that's where you will take the minimum ones. So that's the solution. But there are some caveats. Now, the thing is, you can utilize this zero index a bit more wisely. Okay. Now, what do I mean by bit more wisely? Let's say you make this pair, like you want to swap this 2 with this 4, right? Just assume this. Now, what you can do, you can make this swap easily. That is fine, right? Or maybe let's take another one. Let's say you want to swap this 2 and this 5, right? You can make this swap easily. You can make this 5 and this 2. That is okay. But you can utilize this 4 as well in the middle. What you can do is you can swap this 2 with 4 initially, and this will become 2, and you can then swap this 5 with 2. So this will become 5 and this will become 2. So this kind of operations also you can do, right? And because you can do this kind of operation, you can save one operation at least when there is only one value here. Let's say there is only one 4 remaining. If there's only one 4 remaining, you could have arranged this, you could have taken one pair which were already forming and rearranged them in this fashion. Like, so in that case, you will be adding 0 to your answer. Like currently you are adding 3 and 11, right? But in that case, you will be adding 0 and 3 to your answer. And that would be much more optimal, right? So that kind of cases are there. Now, how to solve that kind of cases is something which is greedy. Now, why greedy? Like, why not you don't need to apply this entire logic at all. You can just choose a greedy approach and that would work. The greedy approach is, if the maximum value here, let's say maximum is m, if if 2m is greater than the total sum, right? If 2m is greater than total sum, then only you will take something from here. Otherwise, you will not take anything from here. Now, why this works or what is the proof against this is something I would not explain here. Truly, I myself didn't completely understand it, so that I have the intuition, but I'm not fully uh, confident about the solution or the approach. So that's where I will ask you to look at the ICPC regional online round contest, online round problem reduction game. This was there in 2018 when I gave it, and this problem was very similar to the problem we are trying to solve. And there is a very nice editorial on this as well. So you can go to the editorial of this, and there is one similar problem which is Shefuni. Like Shefuni is the code of the problem. You can just search it, and this is also very similar problem. You can look at the this particular editorial as well. I will link all of this in the video description below. But again, I would not want you to take this an exercise, because this is something again is an ad hoc problem, and this kind of problem you will be able to solve only when you are aware of these constraints or this kind of logics already. So with that, I hope you get some basic intuition of how to solve this problem, right? And now you can go through any of the codes that is already out there, and I am sure you will be able to understand the crux behind that solution. If you have any doubts in the problem, please post them in the comment section below. I know this is a bit involved, so feel free to post the doubts. I will try my best to answer them. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you tomorrow. Thank you.